Professor Proctor. You can start when you prefer.
Thank you so much, Jose, for your very kind introduction. And thank you again for inviting me to come and lecture. Today you see me in my home office, and I guess most of you are also in your homes following this. I would have loved to be in Granada, but things aren't always the way you like them to be. So right now you have sunny weather, perfect temperature, whilst I'm in Norway, and it's right now it's raining outside. We have about, let's say about 5 centimeters of snow. It used to be close to 50 centimeters, but the rain has just eroded it all away, so it's like full of slush and terrible. But I have good spirits to come and lecture you a bit today on GPU computing using Python. So that's going to be the big thing today. As Jose said, my name is André Brokker, and I'm the head of the mathematical modeling group. We are about 17 or so permanent employees at the OsloMet University. And we do everything from physics to chemistry to high performance computing, but everything related to mathematical modeling. And that's sort of the topic that I'm also very interested in. So my background is in the intersection between like mathematics on one hand and computer science on the other. So I'm in like the overlapping field there. And if you then have the knowledge of computers through the computer science and you have the knowledge of mathematics, you sort of have a hammer. And this hammer is something that I want to go and hammer nails with. So I'm looking for problems to solve. And every time I find an application area where I want to solve something, essentially what I do is try to solve something more accurately or faster. Those are the two things. Everything I do is about solving things more accurately or faster, if you boil it down to the bare basics. And it's a lot of fun, but it takes a lot of work as well. Now, I would like this to be a very interactive session. So first of all, I'd like to say hello to all of you, sort of just to warm up our voices, because you're going to just fall asleep if you listen to my voice just as monotonous going on for hours and hours. So, good afternoon, Luis Miguel. Do you use both names?
Yeah.
So, hello. Very nice to say hello to you again. And good morning. Good afternoon, Pedro.
Good afternoon now.
Yeah, it's afternoon. Good afternoon, Pedro.
Good afternoon, Andre.
And good afternoon, Daniel.
Good afternoon as well to you.
And good afternoon, Alfonso.
Good afternoon.
A bit of feedback there. Wow, excellent. Now you pass like the chat GPT test. I know you're all humans, more or less. Okay. I would very much enjoy it if you guys stop me during the lecture and try to ask questions. If you don't understand something whilst I'm talking, I would be honored if you raise your voice and say, Andre, can you please explain? I don't understand. Are you all okay with that? Just give a thumbs up or whatever. Perfect, Luis Miguel.
Perfect.
Excellent. Okay, then we have an agreement. You will stop me when you don't understand. Today, I guess you have all seen the web page that is set up for this course. So it's here. It has video recordings from 2021, and you see it's more or less the same visual profile. It's the same background, same sort of covered in those videos, and me as well. And they will cover more or less the same topics that we're going to be covering today. But the reason I'm doing this live is I want to give you something else. I want to give you something better than the videos. Because watching those videos, maybe it takes a lot of effort. If you watch a video, it's sometimes it gets a bit difficult to follow along. For me, at least, I find it much easier to follow a lecture which is live, than following a lecture on YouTube. If I follow something on YouTube, I often fall asleep. It's kind of embarrassing to say, but that's the truth. So today we're going to be covering some of the topics which are on the webpage that I posted. First, I'll give you a short introduction to this short course that we're having today and tomorrow. And then I will give you a short introduction to CUDA using Jupyter Notebooks. And then I'd like to ask all of you, have you used Jupyter Notebooks before? I'll write what it's so you...
Yeah.
Yes. Yes.
Excellent. So you are actually using... are you using CUDA from these Jupyter Notebooks or just anything?
No, CUDA.
No, we are using C++.
Good. So then hopefully you'll learn something today. So I'll go through... I lost my pen. I'll go through an introduction to using Jupyter Notebooks to actually run some CUDA programming and use that as a development tool when you're working with high-performance GPU computing. And then we'll go into a practical example. And that's going to be to compute pi, which is like 3.14159 something. Computing that using Monte Carlo integration. Now that's a perfect example which fits the GPU nicely. We'll go through an optimization stage there. So we'll start off with something that we just understand as a simple CPU code, and then we'll make it more and more advanced and more tailored towards the GPU so that it runs efficiently. Finally, we'll end up with some floating point challenges. And this is really important. Things like 0.1, the number 0.1. If you try to store this number in a computer, it's impossible. We'll come back to this later today. So you'll hopefully learn why 0.1 is impossible to store on a computer. And then at the end of the day, I will be giving you some homework. And that is essentially to install some software. Have any of you used Anaconda before?
Yeah.
Yeah.
Excellent. So at least 3 of you have used it before. Thumbs up. I have made an environment file, so you should be able to run conda env create with this file that I've given you. And then you're done in like 10 minutes with the homework for tomorrow. And then after the course of tomorrow, you'll have a bit longer homework, but we'll get a good start today and tomorrow at least. Whew. Okay, that was an introduction to a bit about me and also a bit about the course today. And tomorrow we're going to continue, and the topics for tomorrow are also available on the webpage I've linked to. And we're going to go a bit through best practices for scientific computing. And then we'll go through the main, sort of the diamond in what I want to teach you, which is physical simulation using GPUs. And that's kind of my PhD topic and something that I've been working on for a very long time, using GPUs to run physical simulation. And the cool thing about it for me is that I can create animations. I can create things like water, explosions, these kinds of things. So tomorrow, if we are lucky, we'll be able to get all of you guys set up with your own simulation network, running simulation software, running on your own computers, where you can experiment and create your own videos. That would be like a very, very good thing for me to get out of this. And then I'd like to ask you guys, what would you like to learn? Perhaps it's a bit open question, but is there anything special that you are like, oh, I would like to, this is a topic that I would like to learn or discuss a bit related to what I've said already now? It's kind of difficult to answer, right? Because you don't know exactly what I'm going to talk about. But if there's something that you're thinking about, please let me know as soon as possible, or when you come up with it, that there's something. Okay, Then I would like to just well, let me first ask. In the course so far, I believe you have mostly used C++. Is that correct?
Yeah, C language.
Yes, C or C++. Perfect. So today I want to transition us over into Python. How many of you've used Jupyter Notebooks? So I'm assuming that you know Python, but just to make sure, are you all familiar with Python?
I'm familiar a bit because in Italy we did operational research exam, like for optimization. We used Gurobi framework.
Yeah.
I don't know. Yes. So that's it.
And what about the rest of you? Please feel free to chat also and say that you know this or don't.
Yes, me too, because me and Daniele are colleagues from Italy.
Cool. So
Me too. I did it on a signature of cryptography.
can you repeat that? You were working with...
Last year, I took class of cryptography.
Ah,
So we did it on Python.
very good. I would actually like to take a class on cryptography myself to learn a bit more than I know already now. What about you, Luis Miguel?
Yeah, I took some classes related to business intelligence and AI. So I know a bit about Python and the libraries that it has for that topic.
This is very, very good and very interesting to see the wide areas that you come from: operations research, cryptography, and business analytics, and AI. Good. Today I will try to make the connection between CUDA and Python using the Jupyter Notebooks. So let me just start off. I have installed the software installation already in my my computer. So let me try to move something like this. Can you see my screen now?
Yes.
Very good. And hopefully if the quality is not too good, let me know. All right. So this is the webpage of the course, and you can see here the software installation. So you need to have the CUDA drivers, the CUDA toolkit, and I think you all have that, and then the Anaconda or Miniconda, which you can install. And the easiest way to do this is to get the NVIDIA toolkit. We're using apt, which I assume you have, and then Anaconda. Just follow this along, and then create the environment, and then you should be able to run Jupyter Lab. And by doing that, you should get something like this. So let me open the right window, or drag it over to you, so that you can also see it. Sorry for it's. I'm just trying to move my windows or organize my windows so I can see you guys a bit, so I follow what there. But Google Meet actually flips my screen, so it's really difficult to try to navigate. Okay, but this is the I'm supposed to go. Yeah. Let me open a new window here. I was in some work on this server already, but if you open Jupyter Notebook, you should get, okay, it doesn't want to open a new one. Let me just close all of these. So as you see, I have a lot of tabs open. And this is like simulator, untitled, animate satellite, a lot of different things. Okay, you should get something like this, and you will have a an environment called GPU env. And working with this, you will get something which looks like this, which is I cannot. Let me see if I can hide this. There. So this shows just a Jupyter notebook essentially. Now, what I've done already for you is that I have created this environment file. And if I click this environment file, it shows you what it's actually installing. So when you install this in your homework, it's going to install all of these packages into a separate environment that is called GPU env. So it's going to have the CUDA toolkit, it's going to have some IPython kernel, it's going to have Jupyter Lab, so you can run Jupyter Lab, Matplotlib for plotting, NumPy, and then come some interesting ones, PyCuda and PyOpenCL. We're actually not going to use the PyOpenCL in this course, but I leave it there so that you have the opportunity to look into that as well. It's similar to PyCuda, and if you look at the videos from on the webpage, they actually go through some of the OpenCL versions as well. Then we use a recent version of Python, SciPy, Pandas, and PyTest. So we'll go through some of these throughout the lecture material. Okay, now this is the simple Jupyter notebook, and here I can do some printing. So this is just regular Python scripting essentially, which you enter cell by cell, and you can do things like I is equal to 9 into a cell, and then you can do I is equal to I plus 2, and then you can do print I, and then it should give you 11, right? Okay, so let's run cell number 3 here once more, and then it gives you 13, and then it gives you 15. So I can run this in multiple times, and now you see it's the cell counter is already at 10. And this shows that if you're reading through a notebook, there is a chance that what's written there is not what has been executed. Because what's actually been executed by the Python interpreter now is something like this. So we started off with 9, and then we add 8 more to it to get to 17. So this was actually what was going on in the Python interpreter, even though the code in our Jupyter notebook looked like this. So every time we execute a cell, it changes the state of our Python interpreter. Now this can become quite confusing as we go along. So one trick to keep in mind is that we can do something like kernel, restart kernel, and run all cells. So this is very helpful when you're working with CUDA, because you're working with CUDA and you're developing a GPU kernel. And then at some point, if things are a bit more complex than what we're seeing here, you don't really know what's going on, and you have a bug, and maybe the bug is because you did something like this, execute a single cell multiple times, and then you get an unexpected result here. So sometimes it's good to just go to the kernel, restart kernel, and run all cells. And then it gives you the expected result that you're looking for, 11. Okay, I'm assuming this was more or less easy for all of you, and something that you already know about. Now, what I want to do today is work with PyCuda, and there is a package which I showed you, right? In this file here, I had PyCuda, which was a package which is now installed in your Anaconda environment. So we can do import PyCuda. And now we should have PyCuda something, right? Now I'm going to open my cheat sheet over here so I don't do anything. I've hidden my cheat sheet over there. Right.
Do you have the requirements file so we can install with the pip command all the libraries directly instead of using Jupyter? You can use Python directly.
Yeah, so this you're talking about this this requirement file here.
Yeah, but that one is going to be useful only if you have Conda installed.
Yes,
But I'm trying like to set up the environment directly using Python.
using Python.
Like
Okay. Let me do a short explanation of this. So now we're gonna. Okay, well, we'll come back to the PyCuda stuff, but let me explain to you why we're actually using Anaconda and the reason for it. Okay, so I've got this file here, which gives you some strange stuff, but tells you some packages that are available to install. Let me try to do this. This. Okay, good. Now you can see my hand, right? When you install in your PC, laptop, right? On your laptop, you have Ubuntu. And inside of Ubuntu, you have Python 3.6, let's say, just for an example. Okay. Everything you install there comes with its own dependencies. So let's say you install NumPy 1.17. And you install netcdf 1.3. I don't actually know the version number of netcdf, but something like that. And then you have pandas 0.23. Okay, when you install this, it's all coupled to your Python. So all of these packages belong to Python. And the bad thing is if you break your environment. Let's say you want to do AI, artificial intelligence, and you want scikit-learn in here, okay? Okay, if you want to add scikit-learn into this mix, maybe scikit-learn requires version 1.21, requires version 1.5, and pandas requires version 0.25. Okay, so scikit-learn requires these version numbers because otherwise it's not going to work. Because there's a bug in NumPy 1.17, which is fixed in 1.21. But let's say you have an existing project. So your project A. Your project A requires version 1.17 of NumPy because there's a function in 1.17 that was removed in 1.21 because they're not exactly the same. Then you have the choice. You can either run scikit-learn, your artificial intelligence stuff, which comes from project B, right? Or you can run project A. You cannot run both of them at the same time. The thing that Anaconda solves is this thing. So what Anaconda does is it gives you... Oh, I'm not going to flip this, so I'm going to take a new sheet. So Anaconda gives you let's call it GPU N. This is the one that we're using in this course, all right? It has PyCuda, PyOpenCL, and it has NumPy, and it has Python 3.7 something. Okay, so this, you have PGAP, which runs this. So this is the project that we're running, right? So project PGAP. This class. You can at the same time have the base environment with Python 2.7. For example, let's say you have some legacy code that doesn't work anymore without Python 2, because there's a very big difference between Python 2 and Python 3, a very big difference. So there's a big cross, they are not compatible. So let's say you have some old project that can only run Python 2.7, then you can have base there and you can have GPU-env. And the cool thing about Anaconda is that you can use both. So you can say that I'm going to run project A with this one. We're going to run pgap with this one. And we can have another one, which is called deep learning. And this one may have the scikit-learn up there. Okay. So what Anaconda does for us is that it enables us to have different environments. And this is like virtual machines. They're independent. So you can have Python 3.8 here, Python 3.7 there, and Python 2.7 there, and you can mix between them. So that's a big reason behind this. So let me bring that back to your question. Can I just install this in my Python distribution without using Anaconda? And the answer is yes. Go ahead. But you may end up breaking something, as I said here, and then you'll get some error messages which say that well, dependency cannot be met, conflicts between package versions, and so on. Okay, did that make sense to you guys?
Yeah.
Good. So this is the reason why I want you, or I suggest to you, to use the Anaconda toolkit. It's not a toolkit, but use Anaconda to set up these environments. Just follow the recipe on my webpage and you should be good to go. It should take about 10-15 minutes. Okay. Please.
Yes, another thing, but I don't see the point of, I mean, I don't know the difference between Conda, because, for example, Python, it already provides some functionality to create virtual environments. So, and you can provide even the version of Python that you want to use. So, which one is the difference of using Conda and using the virtual environment command that provides the Python library?
If you are an expert in virtual environments with Python, feel free to use that. I'm not the expert there. I've used virtual environments in Python before, and for me, it appears cleaner and more manageable to use Anaconda. So I've been using Anaconda actively for my research projects and my development projects. So this has been used both for industrial level code and for my research code. So that's why I use it. If you know how to use virtual environments in Python and that works for you, thumbs up. You have the list of requirements is here. Just install it. Okay?
I will follow your guide.
Perfect. And
Sorry, just
Yep.
another question. If we have a Windows system, can we use a virtual machine for Ubuntu and the Linux system?
Very good question, Alfonso. No. The reason is we're using the GPU, and the GPU cannot be virtualized. But I have good news for you. Use Anaconda and it works. So by using Anaconda, you can actually get the same, you will use the same environment file, this GPU YAML. Install that one, you'll get the, you have some more GUI things in Windows than you have in the terminal in Linux. So you'll just click a bit about and you'll find out how to use it. So right now I'm on Windows and I use Anaconda to manage my virtual environments here.
Perfect. Thank you.
Good. Then, so that was like a digression on why we're using Anaconda, and hopefully useful to you guys, because this is really important. And as you saw from this file here, it gave a couple of versions here, which means that when I ask you to install this, I know that you're at least having PyCuda, which is more modern than 2021.1. So you have a recently modern version, so I can assume that you have the same functionality as me. So we're not going to have the issue of you running a version which doesn't have the functionality that I'm using. So we'll have the same platform and we'll have the same functionality. Okay, let me jump back to the code that we're going to go through. And I think we're going to have a break a bit about 6 o'clock or something to get stretch our legs and drink some coffee or similar. Just so you know. If you guys are just really falling asleep, let me know and we can do a break before that, or yeah, just let me know. But we were here. We were I'm just resizing my presentation window here. Good. So I did this import PyCuda. Let me do the screen size a bit larger so you can see. There. So this package now seems to work. At least I can import it without any error messages. This is the first thing to test, that I can import the package. And now I'm going to run you through the hello world version of PyCuda. So this is just taken from the webpage of PyCuda. So if I Google PyCuda, it's going to give you the welcome to PyCuda's documentation. It gives you like an overview of the package, and it gives you some like a tutorial where it goes through the stuff. So this is essentially what I'm going to cover now. So if you think some things are a bit unclear, this is the source to go to as well. But please ask me instead. Okay. In CUDA you have both you have the driver interface and some other interfaces. And now I'm going to follow the tutorial where we're using the driver interface more or less. So import PyCuda driver as CUDA. Good. Still no error messages. And then, if you remember from your C++ work, you need to initialize the context of CUDA and all of these things to make sure that you can access the GPU. Now we can actually get some help from PyCuda to do this automatically for us. It just selects the GPU, sets up a context so that we have everything ready to go. So I'm going to use this today so that we have less hassle of selecting individual GPUs and so on. And actually on this machine that I'm running now, it has two GPUs, so I don't know which one it's going to select. It's just going to select one of them. So from PyCuda compiler, and there, just as a side note, right now I'm using the tab auto-completion to just see what I can do. So this is very, very handy when you're working with the Jupyter Notebook, because I often tend to forget some things, and then, okay, it's not going to be CUDA, but it's going to be compiler that I'm actually looking for. Import source module. Now the source module This one is the one that helps us compile our CUDA kernels. So what we're going to do now is we're going to have some data in Python. We're going to move it over to the GPU. We're going to run a kernel on it and get the data back from the GPU. So it's just a hello world example. Right. This just imported the CUDA stuff, and let me just try to merge these cells, merge above and merge below, so it looks a bit nicer. I like my import statements to look something like this. And I'll comment import CUDA PyCuda and specific submodules. Right, and then as I said, we're gonna get some numbers on the GPU. So we'll start off making them on the CPU. Import NumPy to generate numbers on the CPU. Okay, have you used NumPy before?
Yes.
Yes.
Ah,
For that test.
good. Yeah, just very good to know. Okay, so NumPy gives us access to like matrix notation to data, so we can have multi-dimensional arrays and so on. Now I'm going to generate some random numbers here. So I'm going to call a is equal to NumPy random. Okay, so this is just my NumPy array filled with some random data. Now I can do print a.dtype. This is going to give me float 64 numbers, double precision numbers. So let's note that down here. A is a double precision array. Okay, just keep that in the back of your mind. I'm giving you a hint already now. So let me just add some, first generate some random numbers on the CPU. Okay, and now what we want to do is transfer the data to the GPU. Transfer the data to the GPU and allocate data there. And now hopefully you'll see how much easier things are in Python compared to C or C++ when you're working with it, because like doing all of this is going to take a lot of time on the if you're using C++, but in Python it's like 3-4 lines of code and you don't have to compile the program or anything. So let's call it a GPU is equal to CUDA mem alloc a.n bytes. Let me just do that as well here. So I'm going to insert a cell here, print, or I can do it here, print some information about A. So I'm going to print the data type, print a.n bytes. So this is information that's already in the NumPy object here, okay? So it has 128 bytes and the values are 64-bit floating point numbers. And let's just double check if that makes sense, right? So we have double check size if size makes sense. So we have number of elements, a num elements, that's 4 multiplied by 4, right? So it's 16 numbers, and then num bytes per element. That should be, okay, so a double precision number, that's 8 bytes. Do you agree?
Yes.
Thank you. And then we're gonna just print the number of bytes. Okay, so we got to the same answer. Things look good so far. We have control. And for me, what I'm doing now, this just makes sense for you, right? Why am I doing this calculation? For me, the reason I'm doing this is to show you that it's very easy to double check your own code interactively in Python. So now we check that, well, does this printout here make sense? Let's just double check that it's what we expect it to be. And yes, it seems to be as expected. So what we're doing now is we're going to transfer the data over to the GPU. First, we allocate the data. Oh no, initialization error. What did I miss? Oh, I forgot the auto initialization, right? I mentioned this to you. We need to auto initialize, and then I imported the source module instead of the auto initialization. Okay, so let's add a new. I can just go up and use it here. So I'll add a new. Remember to initialize CUDA. 3 exclamation marks this time. And then I'm going to use import PyCuda also in it. Okay, by executing this cell now, and see I moved it up there so that it's a bit cleaner. It's with the imports. Even though I'm executing it as number 16, I still keep it up there. Let's go back here and see if I can execute this cell number 15 once more and see if it works. Ah, and thumbs up. It did actually work. So now so far I've made my random matrix on my CPU. I've checked how large it is, and I've allocated that number of bytes on the GPU. Now we want to move the data over there. So let's do that already now. CUDA memcopy. Why doesn't... Okay. The tab completion doesn't always work for me. I'm not certain exactly why. So I had to look at my cheat sheet, which is there, to remember memcopy host to device. You recognize this from the CUDA interface. Host to device. So let's write a comment there. Copy data from host CPU numpy a to device. GPU PyCuda a GPU. That's sort of what we're doing. We're moving from the left hand to the right hand. So we're copying a GPU into We're copying into a GPU from A. Works well. Okay. Now I will print out what's in the in this A GPU. Print out what a GPU is. So let's call a B is equal to numpy empty like A. This is just creates an empty array equal in data type and size to A. Okay, so now I'm creating a B array. I'm just copying the data format of A, and then I'm going to copy from the GPU back. CUDA mem copy device to host, and then the format is B a GPU. Okay, and then I will print out. Print B. Okay. Do any of you have excellent memory and see if that's identical?
It seems identical.
It seems good, right? I remember this one. Let's see. Yeah, it looks actually identical. Let's double check. So let's do also print B and then print A minus B, and it's 0. Identical. Cool. So now, if we just look through what we've done, from this one, that's 1 line of code, 2 lines of code, 3 lines of code. I've moved data from the CPU to the GPU and back and included the allocation on the GPU. And this is all operations I think you know already. How many lines of code would you have spent in C++ or C to do this? Anyone?
I don't know exactly, but for sure more than 3.
You're right. It's more than 3. Now, the thing that helps us here is that PyCuda checks for errors for us. So we know that this ran through. We didn't get an error message, so this ran through with success. If you're doing this in C or C++, you're actually responsible for checking error codes and checking that everything works by yourself. So this is one thing that just hides a lot of the complexity of coding directly into PyCuda. Okay, so far so good, but let's do something a bit more exciting. I want to do, now we've copied A over to the GPU, but let's do something with the A GPU before we download it again. I want to create a kernel. So let's first call kernel source. Now these triple ticks, this one, this here, that's a multi-line comment in or multi-line string in Python. So this is very nice for creating kernels because then you can just write your kernel in your code like this, and we can compile it and try to run it. So let's try to write a kernel together now, and feel free to help me when I get stuck doing this. I seem to remember that to create a kernel, you had to have this global keyword, which told the NVCC, the CUDA compiler driver, that this piece of code is supposed to be a kernel which executes on the GPU. Now, after that, you have void, which means that this function is not going to return anything. And then I leave it up to you. What are we going to do with this A, this matrix of 4x4 numbers? What do you think we should do?
Maybe a reduction.
We could do a reduction, but let's keep it simpler, at least for me. We'll do a reduction afterwards in this session, but let's do something embarrassingly parallel. We could double the numbers, or we could half the numbers, or we could add 5 to them. What do you want to do?
Double it.
Okay, so let's do double A. That's my function. It's gonna double A, and now this takes in the array A. And if you remember from your C or C++ programming, that comes in as a float star A GPU. Okay, this is basically the skeleton of our code. Now, what we can do with it further on is to create our index in our the index to this thread in the whole compute grid. So its thread ID is equal to thread idxx multiplied by plus thread idxy multiplied by 4. This is a bit of cheating, right? Because now I'm just saying that, well, multiply by 4 because I know that this matrix has 4 elements. But that gives me the index into this array where I'm gonna index it. So now I can do a GPU of a thread ID is equal to a GPU of thread ID multiplied by 2. And we're done with the kernel. Hopefully I haven't done anything wrong. So that's the source. We want to compile this. And as I said in the beginning, we would compile it by using the source module here. So from the compiler, I'm importing this source module. So that's going to help us compile the module so we get something sensible that we can execute in Python. So we call it a function is equal to a, let's do a module first. Module is equal to source module of kernel source. Creates the source module from the source code. Right, and then we want to compile it. So func is equal to module get function double a, and then we can, so this thing here, get the compiled function double a from the source code. This should compile it, and hopefully we have everything we need to run the kernel. And now let's try running it. So we'll just run func, and then we give it a GPU. That's the first argument. So this thing here ends up as the argument there to the kernel. What else does a CUDA kernel need to have? Do you guys remember?
Yes, the dimension of grid and the dimension of each block.
We need the grid size and the block size. Exactly, Alfonso. PyCuda can help us some. Let's just give it in a block size. Block is equal to 441. Okay, so it's in 3 dimensions. We're just using a 4x4 block. We can also call it grid is equal to 111. So now we're launching a single block with 16 threads. So there's 1 thread for each element up here. Right, 1 thread for each of them. And then we run that, and well, let's check what we should get, right? So this should be 2 multiplied by a minus b. That should be the correct answer, right? So let's see what we get. This wasn't right, was it? Any ideas what went wrong? This looks very wrong. Do you agree? It's like
Yeah.
5, 7. So let's just print A again. So you remember what we were supposed to have. A was nice. And then we get this ugly thing here. Buh. All right. This is the biggest loophole of using of the loophole in safety checks when you're using PyCuda. Do you remember if we go back up, that I said that A had the data type float64? This is actually a double precision number. So A is a double precision number. We're giving it over to the GPU, but we're saying that it's a single precision number. So let's write this down here. This expects a GPU to be single precision numbers, not double precision. Really important to note. Okay, so the thing we need to do here is that we actually need to make sure that A has the right data type. So I can do here dtype is equal to numpy float 32. I cannot do that. I need to do as type. There. Okay, so now I said numpy, convert all of these numbers from double precision to single precision, please. And now if I print the same again, it says float 32. So float 64, that's double precision. Float 32, that's single precision. And that's really important to note. Because if you do this, and we didn't get any error message here, right? You could do the same exact mistake in C++, and you will get this exact same results and strange behavior. But in Python, it sort of tricks us into feeling more secure, because it always helps us by saying, oh, there's an error there that we didn't check for explicitly. It just said that, well, you made a mistake at that point. But let's try to do things again. We just check that the number of elements is correct. So I'll change this to 4. NB, single precision is 4 bytes. Double 8. Okay, so 64 bytes. That makes sense, what I'm expecting up here. Let's do A again, transfer to the GPU again. Compile the kernel once more. So that made everything there. I didn't need to do that again. I could have skipped it. But let's run at least the function again. I run the function, and I run the code again, and it gives me the expected result. All right? So B is supposed to be double, and I checked here that it actually is the double one, and it gives the expected 0 sum at the end. Okay, so I'd like to ask you, was this useful so far? Did you learn anything?
I think so.
Okay, so let me ask you, is the pace too fast or too slow or okay?
For me, it's okay.
For me, it's okay, but it could be difficult if I have to do it from scratch after seeing this.
Yes.
But I get the whole idea.
And the video is being recorded, so you can rewatch it and see what's going on. But good. So this was the Hello World section. I spent a bit more time than planned on this section. But the next section, so I think I want to conclude this here and say that, well, what we did was that we used PyCuda to access the GPU. And through just a few lines of code, we were able to run a kernel and check that the results were exactly as they were supposed to do. And one thing that you cannot do in C++, which is very important, very easy to do here, that is plotting. So let me do that before we move to the next topic, because this is just the power of Python, which enables you so quickly to see bugs and things that are off the scale that is really difficult to do in C++. And keep in mind, I've spent more than 10 years working with C++ and CUDA, so I know how to navigate compilers and GCC and compiler flags and NVCC and all of that. And I'm starting to love using Python because it makes me more efficient. It makes me write code which is better in a shorter amount of time. And the plotting in Python is really one of the things. So import matplotlib from matplotlib import pyplot as plt. This just gives me immensely powerful graphics at my fingertips. So plt plot 8. see how that line turns out. Okay. Okay, it doesn't work with legend like that. So it gave me 4 lines. Let me do a of 0 like this. So this is just plotting a single line of the matrix A. And then I can do the same with B. PLT plot B of 0. Okay, and then I need to do label equals A, B. And then I do PLT legend, and then PLT title, publish this graph. Okay. What I showed you now was that in these 4 lines, I created something which is the same way that I'm using creating figures that I go into publications. So if I'm writing a scientific journal article, I will be using the same tools as this to just look at it. And now if we look at this, we can very easily see that, well, B appears to be twice of A, also for negative numbers. So this was something that I didn't think about when I wrote the code earlier on. I actually have negative numbers in my A matrix, and they also seem to double, right? So that's just easy checking. So let's say I did something wrong. Let's say I did +1. If I do that calculation, which I did up here, multiplied by 2 + 1, I get some strange results here. It's not very easy to see what's wrong here, right? I get some strange things. But if I plot this again, it's perhaps easier to see where things have gone wrong and start investigating. Okay. That was the introduction to Jupyter notebooks working with PyCuda. So I'm going to rename this notebook to Hello World PyCuda. And that's the first version of working with the GPU through Python. And tomorrow, after you've installed all of the Anaconda stuff, we will be doing this interactively together. Well, we'll start off with some notebooks, and we're going to create some cool simulations. Okay, right now it's about 1740, and I think perhaps it's good to have a break about now, because the next topic is computing Pi in parallel. What do you guys feel? Either I can do the introduction to the next section now, and then we have a break before we go into the code, or we can have a break now and do the introduction and the coding in one go. What do you guys want to do?
For me, it's good to do the introduction now and after into the code.
Excellent.
Yeah, for me too.
Yeah, for me as well.
Ah, very good.
Yes, for me too.
Nothing's better than unanimous responses. Okay, so let me go into the next topic. Okay, so here is my cheating schedule for today, right? So far, we had an introduction about the course. We did some unplanned stuff about Anaconda. And then we did the Hello World in Jupyter Notebooks. And the next thing is computing Pi in parallel. Okay, so Pi. If I draw a circle here, and apologize that it's not the perfect circle, we have a relation which is between the circumference and the radius. Okay, so we have R there, and we have the circumference, just let's call it C. Okay? So the circumference is 2 pi multiplied by r. C is equal to 2 pi r. Hopefully you remember that from mathematics at some point in time. And pi is equal to 3.14159 something. Okay? It's not important what something is. It goes on forever. But we have this relation. So if we take r and we try to wrap it around the circle, we get 1, 2, 3, 4, 5, 6, and I did it a bit wrong. Something like this. So that's 1, 1, 1, 1, or it's R actually. R, 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 and then it's 0.28 3 something R. Okay? So that's the definition of R. The definition of pi. What I want to do is I want to estimate the value of pi by using Monte Carlo integration. So this is just a bubble in my notes. Just so that we remember what these things are. And then the topic now, which is Monte Carlo integration. Now, Monte Carlo integration is an immensely powerful tool. It's being used every day to do really complex things. Let's start off with the word integration. And can you read my handwriting good enough?
Yes.
Good. I have terrible handwriting. Both my parents were doctors, so they're used to writing prescriptions, and it's a nightmare. So I've inherited their poor handwriting. But let's look at this word integration, right? You may remember something from high school curriculum, which looks like this. You have your axes, which go like this, and then you could find a graph. Your graph would be perhaps something like this, and you would select a point A and a point B, and you have this f of x, that's your graph, right? And then if you would do the definite integral, you would get something like this. So the I'm sounding like a robot. The DDD, like a Morse code. What you get here? That's the integral from A to B of f of x. Okay. Now this works very well in one dimension. So this is 1D. It works excellent in 2 dimensions. It works horribly in 100-dimensional or 1,000-dimensional space. If you're trying to approximate this to a numerical integration. You can approximate this because sometimes you cannot really know what this f of x is when you integrate it. So it's sometimes impossible to find the antiderivative, and then you do it numerically. So you use Euler's Euler integration essentially to approximate this through let's say the midpoint rule, trapeze rule, and so on, Simpson's rule, to find some sort of estimate of what the function is. And that works very well in 1 dimension, 2 dimensions, 3, 4 dimensions. But if you're up to 100 dimensions, 1,000 dimensions, you get into the curse of dimensionality. So let's 100D, 100 dimension, that's a big crossover, because we cannot do that. That's the curse of dimensionality. Okay. Now this curse of dimensionality means that if you're trying to solve this integral, it becomes computationally too demanding to solve for a high dimensional space. The good thing is that Monte Carlo integration works perfectly. Monte Carlo integration tries to solve this, tries to find the area under the curve, which you remember, but in a different way. So it doesn't approximate this through like the traditional numerical integration. Then you would have something like these bars, which you may remember, right? You would do the squares where you would try to say that, well, the area of this curve is more or less the same area as under these bars. And that's the thing that doesn't scale to a 100-dimensional space or a 1,000-dimensional space. But Monte Carlo integration does it in a different way. So if we have the same kind of example here, if we do this for Monte Carlo, let me just draw a this in a thought cloud again, break it up a bit. 1D, so this is numerical integration. That doesn't work for 100D or 1000D space, but Monte Carlo integration does. And it does something similar. Okay. In this one, we approximated the curve by these rectangles. Now, what Monte Carlo integration does instead, if we have the same kind of curve, so this is our f of x, and we have our a and b. What Monte Carlo does is that it just randomly picks some points. Okay, how do you randomly pick points? Well, let's say we do this point, we do a point here, we point there, and a point there. Okay, they're randomly placed, so they're supposed to be uniformly distributed if you have sufficiently high number of them. And what you then do is that you say, well, I'm gonna say that, well, I have a value here, a value here, a value here, and a value here, and a value here. So I have all of these point values. Okay, so this is f of x1 up until f of x 1, 2, 3, 4, 5. Right? So this is x1, x2, x3, x4, x5. And then I just basically say, well, I sample these 5 things, and let's just say that the integral from a to b of f of x dx, well, I'll call it Monte Carlo MC. Let's just say it's like 1 over 5, and the sum I equal to 0, 1 to 5 of f of xi. So what I'm doing is I'm just saying that, well, I'll plus the 5 values. I'll add them together. So it's going to be f of x1 plus f of x2 plus f of x5. And then all of that times 1 over 5. And then you'll get sort of the average value. One thing I forgot is you have to multiply by the distance here. Multiply by b minus 8. So you actually get the whole area under the rectangle. But what you're doing is you're replacing a regular sampling of the whole domain by some random stuff, and you're just calling some sort of average. So this is greatly simplified, okay? But that's the general idea. Did that make sense to you, or was it a bit too mathematical?
It's clear.
Thumbs up, Daniel?
Yeah.
Thumbs up.
I didn't quite hear you, Daniel.
Sorry for the microphone. Everything is perfectly clear.
Good, it's clear. Okay, so you do some average. Now the cool thing here is that this one, there's a ton of research into doing this in the best way, and you can get really accurate results, but you have the curse of dimensionality. For the Monte Carlo, it's very easy to do this in higher dimensions. You just pick random points in your 100-dimensional space, and you evaluate your function at that point. And when you find the value of that, you add it to your averaging scheme. So somehow you average this. So let's go back. Let's draw that also into this thought bubble stuff. Okay. Let's go back to the original thing, which was this pi. We want to estimate pi with Monte Carlo integration. And why I'm actually dragging you through this mathematics stuff here is that I want to give you an idea that this is actually something which is worthwhile doing, even though we're doing something stupid. We're trying to estimate the value of pi, which there are tons of better ways of doing than what we're going to do now. But the technique we're using, Monte Carlo integration, is used in ray tracing, it's used in medical imaging, it's used all over the place. And the common denominator for places where you use this is high dimensional problems. So high dimensional problems always give you sort of Monte Carlo integration as the go-to tool for solving it. So let's see how we can estimate the circle, a circle's area, or we can estimate pi from this. Let's go back to the drawing board and draw up a circle. Okay. Whew, this is a terrible circle, but yeah, it looks more like a squished pizza, but it's good enough for what we're doing. Let me do this one, so it's slightly better down here. Okay. What I want to do is to use not what we used earlier was that we had the circumference C was equal to 2 pi r. But what I want to use now is the area. So the area, capital A, is equal to pi r squared. Okay. This is my circle. This is my relation between pi and the radius and the area. Let's simplify things and say that this section here is equal to 1. So the radius is equal to 1. So that gives me that the area is equal to pi, more or less. Do you agree? Hopefully I haven't made any mistakes. Okay. So the area is equal to pi. So now what I need to do is estimate the area of this one. And the cool thing here is that this is an irregular shape, right? We could compute the area somehow, but what we're going to do now is we're going to play darts. So we're going to do play darts. Right? So we're going to throw these darts onto our dartboard and see where they hit. So we hit one dart there, one dart there, and this is random placement of darts, okay? So we're not trying to hit the center, we're simply just throwing blindly the darts at the dart table and hitting these points. Okay. The thing here that can help us estimate the area of this circle is finding the relation between darts that hit the circle and darts that fall outside the circle. Okay? So let's first restrict our thing to a more rectangular domain. Okay? I should grab another color actually. Let me try black. Okay. There. Okay. From this, we have a bit more information. Now we know that this is this section here is 1, so this section here is 2. This section here is 2. And then I'll remove the darts which fell outside of the circle, outside of the square, because they're not going to count. And now what we're doing, we're throwing darts all the time. And if you continue this process, throwing an infinite number of darts, and then we count the darts, then essentially the darts here inside the circle will cover the circle completely, right? So they will essentially just be completely mapping out the inner circle, whilst the ones which are outside cover these corners here. So what we're doing is just counting the number of darts inside. So let's write that up. How many darts inside circle? That's the one of the questions. And then the other one is how many darts in total? Question mark. Okay, let's start with the second question. How many darts in total? We know that if we just have an infinite amount of darts covering the whole domain, that should give us an area is equal to 2 multiplied by 2, which is equal to 4. Okay? But the number of darts inside the circle, so that's, let's call it A2. A2 is equal to this. And then A1, that's equal to pi. That's the area inside the circle, because we had this this relation up here. which should be there. So what we want to do, this should be, so how many darts in total? That should correspond to 4. How many darts inside the circle? That should correspond to pi. And now by simply counting the number of darts we have in total and inside here, and the 4 here is the one that gives us the reference points, right? We should be able to get a pretty good estimate of the number of points inside. Was that more or less clear?
Yes.
Thank you, Daniel.
Yes.
Thank you, Pedro. Okay. Because then I think, keep this in mind. What we're trying to do is we're throwing these darts into a 2x2 circle. We're going to simplify this in a second. And by doing that, we're getting an estimate of pi, just by counting the number of darts which were thrown and the number of darts which fell inside the circle.
Sorry, I have a question.
Please.
And in order to obtain the area of the circle, it should be pi. We need to know the area occupied by each dart, right?
Yes. Very good question. So to get the estimate of pi, we need to know the area, as you say, for each dart. And this is quite... let's say that we throw 1 dart. Well, what's the area of the dart then? Well, the area of the dart in that case is 4. Because that's our whole domain. We have to cover our whole domain. So that's our reference point here. If we throw 2 darts, each dart corresponds to an area of 2. If we throw 100 darts, or let's say 400 darts, then the area of each dart is 0.01. Right? Because then you just multiply 0.01 by 400 and you get 4. And we're using this relation between 4 and the number of total darts to estimate pi.
Right, now it's clear.
Excellent, Alfonso. So that's a very good question. Okay, so it's 6 o'clock now. So I suggest we do a 50-minute coffee break. It's a bit too late for coffee for me. I have to get sleep in the night because of my small children, which wake me very early. But I suggest we take a coffee break for 15 minutes and meet here again at 6:15. Okay?
Great.
Okay.
Great. See you in 15 minutes.
Yeah.
Yeah.
Mm.
Okay, welcome back, everyone. I hope you're back. Are you guys here?
Yes.
Yes.
Excellent. It's good. It's it would be a shame if I would just start speaking for an empty audience. It's much better to know that you're here. Okay, so we were discussing this estimate of pi using Monte Carlo integration. So let me just move over to that again. So we had this estimate, we were throwing darts, and I think it was you, Alfonso, who said the area of the dart, or at least Alfonso Pero had the question about what's the area of the dart. And that's one of the key points here. So let me simplify this a bit and say that we're going to just look at the area which is here. Because this is symmetrical, right? It doesn't really matter if we cover the whole circle or we just cover a small section. But well, it doesn't really matter. Let's come back to that. We had this relation that the area 2, that's the total. So let's call it AT for total. That's equal to 4, and area inside AI. And that's equal to pi. Okay? So let's move the AI up there also like that. Okay, so let me now get that in a second portion over here. So we have AI should be equal to pi. And we have, that's area inside, and area total should be equal to 4. And the area inside should also be approximated by the number of points inside. And the area total should be approximated by the number of points in total. Okay, so that brings us to the area of a single dart, which you mentioned. So AD, which is the area of a single dart. It doesn't, yeah, let's think of it like the area of a single dart. You can think of that as, well, this relation here. So if we have the area 4 divided by the number of darts in total. Okay, that makes sense, right? If we throw one dart, the area of the dart is 4. If we throw 400 darts, it's 0.01 for each dart. So let's then say that the area inside here, so area inside, that should be equal to the number of darts inside multiplied by the area of each dart, right? This sort of makes sense. Each dart has a certain area, and we multiply by the number of darts which hit inside. And that should be, or the area inside is approximated by, let me do approximate there, which then is equal to number of inside multiplied by, well, this area is 4 over number of darts in total, which is equal to 4 multiplied by the number of darts inside over the number of darts in total. So area inside is equal to this, or is approximated by this. So if we take these two together, we say that, well, we should get pi by just counting 4 multiplied by the number of points inside divided by the number of points in total. Okay, let's look at this this quadrant over here. It's going to be quite simple. Okay. If we throw a single dart we can find this area here by Pythagoras, right? So the r here is equal to the square root. Let's just So it goes here. So that's x1, y1. So x1 squared plus y1 squared. It's just Pythagoras, right? We create a triangle and then they find the radius there. So if r is less than 1, because the radius of the circle is 1, then we count it as inside. Else, outside. And that's the whole thing. So I've gone through a whole lot of stuff motivating this. We ended up with counting the number of points inside versus the number of total points. And now we have a way of calculating the number of points inside. We just check if the radius is less than 1. If it is, we count it up, and we multiply by 4 to get the estimate of pi. Okay, are you guys ready to try this in source code?
Yes.
Thank you, Alfonso and Daniel. I was hoping for yes. It was like a leading question.
I have a question.
Please.
Let's take that we don't have any kind of limitation in computing resources. Which method is better, like the Monte Carlo integration or the numeric one?
That's a very good question. Let's say we have an infinite amount of computing resources. I think that at some point you will get into floating point problems, whichever method you're using. But in general, for low dimensional problems, you want to use numerical integration. For high dimensional problems, you want to use Monte Carlo methods. I think that's a good estimate, but given infinite amounts of computing power, you have more rigorous theory related to the numerical integration versus the Monte Carlo one, because the Monte Carlo method is a stochastic method. It depends on these random points. If you start the experiment once more, you will get a slightly different location of all your darts, and that means that you'll get a slightly different area for pi. It's still just as good estimate, but it's different. So every time you run the experiment, you'll get a different estimate of pi. So yeah, if you were to force me to choose one, I would perhaps say numerical integration, but it has its issues. So realistically, low dimensional numbers use low dimensional problems use numerical integration. High dimensional use Monte Carlo. Okay, let's move this into source code. So let's move over to the screen there. Excellent, and we are back in our regular folder, and it's not there. It's not a new folder, but I want to do a new launcher. Good. Okay, so I'll create a new launcher, which means just a new IPython notebook, and I'll just rename this immediately. So computing pi. Okay, I'll start off as before. Import. I'll just copy some of the imports. I will be using PyCuda, so I'll import that. I'm not going to spend time on doing that now. And then again, I will import. I will also import some standard packages like NumPy and Matplotlib. Okay, so that was just getting started. Let's start off by estimating pi in Python. And the thing that we remember from the introduction is that we can estimate pi by the following formula. Pi is equal to 4 multiplied by the number of inside divided by number of total. Okay, and now we need the points. So first generate random points. Do you have any suggestions on how we can create random points? This is the challenge that we have. It's one there, one there. And we want to generate some points here. No suggestions.
Just use the random function, but with the limitation of the one limit in y and the one limit in x.
Exactly, we can use the random function to generate random numbers between 0 and 1. But how do we generate this? There are multiple ways. We can either generate like an angle and a radius, but if we do that, we're going to skew our results because it's not going to be uniformly distributed. So the real or the right way of generating numbers right now is to generate a random x coordinate and a random y coordinate within 0 and 1. So let's try to do that. And I have to do this one. Good. So x rand is equal to numpy random rand. First, let's determine the number of points in total. N total is equal to 100, just to make it easy. There, and then we do the same with y rand. And then we compute radius from origin. And then r is equal to numpy square root of x rand plus y rand, like so. And then we will count the number of points inside. So we can do that in multiple ways. Let's just do a simple for loop. N inside is equal to 0, and then for I in range, 0 and total, if, and then comes the if test that I showed you just now, right? If the radius is less than, or let's do less than or equal to 1, right? That was a mistake on my side. So if it's less than or equal to 1, we call it inside. But if it's greater than 1, we'll call it outside. So that should be relatively easy to check. So if r is less than or equal to 1, so let's do r of I. So because what we're doing here, right, this is vectorized in NumPy. So I'll show you, let's do this a bit simpler. Let's do 10 points, and let's just skip this last one and print things. And then split cell. Okay. So first I'm going to print the random x and y numbers, and they look to be between 0 and 1, and they should be, because the random function is supposed to give us uniformly distributed numbers between 0 and 1. And then let's check the radius, if that makes sense. Print r. Okay, good. Some points are greater than 1, and that makes sense, right? If you look at the first one here, the first point is 0.99, comma 0.88. So that's quite far up in the corner. And I would expect that to have a radius greater than 1, and that's what I get here as well. And then 0.65, that's this point here, which is 0.64, and the y-coordinate is 0.08. So that's quite close to the y-axis, which again brings us to think that, well, it looks plausible that it's actually inside the circle. So this looks plausible in my mind. And then I can count the number of points in total. So if r is less than or 1, r of I is less than 1, we will just do n inside plus equals 1. Else pass. We're actually not going to do anything because we don't count the number of points outside. And then print n inside. 5. Let's look at our numbers here and see how many there are. 1, 2, 3, 4, 5. So things look good so far. And finally, for the finale, let's estimate pi. Pi is equal to 4 multiplied by n inside divided by n total. Print pi. Okay. Best guess in the chat. What's pi with this estimate? Any guesses?
320.
Let's see. 2. Ooh, it's quite a poor estimate, right? We have to do something to make this better. Okay. I will just comment out some of the printing because now we have some faith in our algorithm. So what we just want to do is make it a bit cleaner. So I'm gonna join some of these cells again. So I'm gonna merge below and merge above. Okay. So now we have this single cell. I need to merge this one as well. Merge above. Now we have the single cell which computes pi. Okay. Okay, why does it print the first one? That's the number inside, so I'm gonna skip that as well. Okay, so I run this multiple times. It gives me different estimates of pi. 3.2, that was what you said, Luis Miguel, right? 2.8, so it gives us different results. Let's see how this goes if we do something like 100. Okay, 3.2, 3.2, 3.04, 3.02. Let's do 1,000 or 10,000. Starts getting closer to pi, right? And at one point, it's going to be quite slow. Now it's starting to become slow, right? 3.14, it's still not 15. Okay, so now we're scratching our heads. It takes 10 times as long as last, and it gives us 3.1419. So this for remembering. So how many is that? That's 10 million points. 10 million points. And it gives us an estimate. But you see it converges towards the expected value of pi. Okay, we can do this in a better way. I assume, or you may have heard that using, see, it is my phone just responded to my speaking. You may have heard that for loops are slow in Python. So the for loop here is probably one of the things that takes a lot of time for us. So let's try to replace this one with something else. So I will do comment out this one and do something else instead. And I will say r is equal mp sum mp where r greater than 0. Should be something like this. There. Okay. Greater than or equal to 0. Oh, I did something strange here. Okay, let me fix this for tomorrow and we'll look at that instead tomorrow. Because that's not the total point of this this exercise. Now we've seen that we can do it in Python. Let's do it as a function. So what I'm going to do is...
Sorry,
Yep.
R shouldn't be R minor than 1 instead of 0.
Oh, yeah. Thank you. So n inside should be r less than or equal to 1. Something like this. Okay. Thank you, Alfonso. You see, it runs much faster now. I just replaced some things in the Python code and it runs significantly faster. There's no waiting. So now I can actually run 100 million with this. And I couldn't do that with the old version interactively with you guys. So let's say it was about 10 times faster. But still, it's quite a poor estimate. Okay, so okay. But let's move back to something which is manageable. There, and what I'm going to do is I'll change this to a function. So def compute pi CPU and points. And then I'll just indent everything here. And I'm not going to print pi, I'll return pi. And the number total here is not going to be used. So now just by making this a function, I can do print compute pi CPU 10,000 and it gives us the number. So let's try to make this in using CUDA. So we're going to use the same kind of thing. Now, this is where we need to think a bit cleverly. So I'm going to go back to the drawing board here. And these are the darts we're throwing. Okay, the good thing here about throwing darts in Monte Carlo methods is that it's embarrassingly parallel. We can do this for every CUDA thread. Every CUDA thread can throw its own dart, and we can compute the results as a reduction finally. So this should be able to parallelize quite well. Okay. Let's try doing this in CUDA. In version 1, what I want to do is just make it simple. So in version 1, I would like to just move it over to the GPU so that we have something which works there. Now we have a function which works on the CPU here, but I want to do the same for the GPU. So I'm cleaning up a bit here so that it's easier for us to see. There. Generate random points, compute radius from origin, then compute using the formula. So let's count number of points inside. And then finally estimate pi. Okay. Let me start off by copying this function and calling it the GPU function. Still works, good. And I'm gonna call it GPU. Okay, the first thing we need for a GPU function is the GPU kernel. So let's try making the kernel from scratch. So I'll call it kernel or pi kernel source is equal to and it's the global void compute pi, and then I'll take in a float star inside. Let's just call it inside. We can do something a bit more clever actually. Let's call it, let me jump to my cheat sheet so I follow the same recipe. There it is. Right. And we're not going to use floats because floating point doesn't make sense because we're going to count in this function. We're going to do unsigned int. And remember, when you're passing data into the kernel, it has to be exactly the same as the data on the CPU and GPU. So if you're using unsigned int on the GPU, you need to be using unsigned int also on the CPU. Okay, so this is the compute pi kernel. And the things we want to do here, generate random numbers. So I'm looking down at this comment, right? That's point 1. Point 2 is compute radius from origin. And point 3, check if inside circle. And then perhaps 4, check if inside circle and write to memory. Okay, so these are the tasks we want to do. Let's start off with generating a thread ID. That always helps us. So int unsigned thread ID is equal to thread index x now I need to, you sort of get blind when you're teaching, you know, it's you're teaching but then you suddenly forget what you're supposed to be saying. So let me grab my cheat sheet here. And there it is, good. Because I'm also going to copy some helper code from here. And there. Okay. Thread index y multiplied by block dim dot x plus thread index dot x. That's correct. Please let me know if I do something fishy here. It's quickly done. Okay, so that's my thread index. So then I'm going to generate some random numbers. And then they can be floating point numbers because we're generating coordinates. So float x is equal to something. Float y is equal to something. I'll come back to what they actually are, but let's move to this one. Computing the radius from the origin. Radius is equal to square root of x times x plus y times y. Should be quite simple. And then finally check if it's inside the circle. if r less than or equal to 1, then we do the inside of thread ID, right? So we're using the ID up here is equal to 1, else inside of thread ID is equal to 0. Okay, so what we're doing here, if I go back to my document camera, is that we're taking our CUDA threads. They may be in a block, right? So this is thread index 0, 1, 2, 3, 4, 5, etc. And then we're just straightening them out. So this was the thread ID, which is equal to something like this: 0, 1, 2, etc. up to 15. For this case where we have 15 threads. And then for each of these threads, generates X, generates Y, computes R, and then save result. So we're saving the result 0 or 1, depending on if it's inside or outside. So we're saving 0 if it's outside and 1 if it's inside. So what we're getting out here should be an array with all of these 16 different numbers, and we called it the, let me just check what we called the variable inside. And it's going to be 1 for this one, 0, 1, 1, 0, 0, 1, 0, 1, 1, 1. Right? Something like this. So that's what we're going to do on the GPU. Then we're going to do CPU summation. So we're just going to count up all the ones in this one to sum it up to count the total number of points inside. So that's the essence of what we're trying to do now. Let me go back to the source code here. Right. So far, okay? Is it okay so far?
Yes.
Good.
Yes, yes, yes.
Very good. Okay, so that's what we're doing. We're writing to this inside. But these random numbers, if you worked a bit with CUDA, you know that random numbers are really, really difficult. So what we need to do is to cheat. So I'm cheating here by pasting in a function, which is based on Bjarne Strostrup's C++ random number generator. So this gives us a set of pseudo random numbers. And pseudo random numbers means that it's not truly random numbers. It's not uniformly distributed. It can be uniformly distributed, but if you use these random numbers in something like cryptography, it can be hacked because it's not truly random numbers. These are pseudo random. But with this function, we can generate some random numbers. And you see this gives us a random number between 0 and 1. So I can just call the number, call the generator directly. Generate random number, and I'm going to use thread ID as my index into this. So I'm going to call this into an unsigned long instead, or long thread ID. That's because you see this long here comes in as a reference. Okay. I have to, sorry. This is just technical. So long rand seed is equal to thread ID. And then I'm going to do the random seed. And what I'm doing here is just some technical C++ CUDA stuff to generate pseudo random numbers, but it should give us the X and Y, which we're looking for. Okay. So far, I think we're good with the kernel. It does everything that it's supposed to do. So the next thing that I would like to do is make this into a function that we can call from the CPU. And then we do the source module stuff. So module is equal to CUDA, or is it, what did I call it up here? I called it source module. Kernel, and I called it the PyKernel source. Sorry. There. And then the function, let's call it compute pi GPU is equal to module get function, and then it's going to be compute pi, which was the function name. So I always have to map up this compute pi, which is the kernel function, with what I'm doing down here to get the actual function. Okay, so let me, I'm sorry for moving things around there. What I did was split the cell so that I could compile this this kernel by itself. Okay, so we've got the kernel source. With the kernel, we're creating the module and we're getting the function. And it gives us a compiler error. This is good to know already now, at least. Okay, so it gives us something. Okay, identifier R is undefined. Okay. Do any of you guys know what I've done wrong? Identifier R is undefined. And this is important to note when you're working with PyCuda. You get quite a long error message. Always scroll to the bottom, because the thing that you care about is at the last line. It says CUDA kernel line 21. That's the 21 there. We cannot find R. R is unidentified. So if I go back up here, I said, well, this appears to be line 21. We can see if we can count. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. It's 19. And this again comes from PyCuda adding some extra stuff to the top of your source code. So take the line number as an estimate. Don't take it as literally line 21, but about line 21. But what I'm missing here is float. Okay? Because it's not Python, it's C++ or CUDA, which means that I have to explicitly name my strongly typed variables, what type they are. Let me try to compile this again and see what it spits out. Okay, thumbs up. It doesn't crash anymore. So if we go back to our function, which is the next one, all of these things are more or less, or at least these ones, are done on the GPU now. So I'll delete them. We're generating the random points on the GPU, and we're computing the radius from the origin on the GPU. Okay, so let's do that instead on the GPU. Let's call it also inside GPU. And this is where I had to allocate the memory. So I'll jump back here to do the memalloc. It's n bytes. So I'm going to do CUDA alloc, and then it's n points. That's the number of points that I'm using, right? But I have to multiply this by bytes per unsigned int. And bytes per unsigned int, it should be 4.
Okay, jeg fant dette på nettet om iCube before. Ta en titt.
It was my Siri, my phone again, which picks up that I'm saying, asking her for something. Bytes per unsigned int, uint is equal to 4. Now I should be getting something which has sufficient space for every single point. Good. So I have the memory, and now I have to call the kernel. Compute pi GPU, and it's going to take in inside GPU, and it's also going to take the block size. I'm just gonna do it quite easy. Let's do 128.11. Grid is equal to 111. Okay, so this doesn't really use a lot of parallelism. It uses 128 threads in a single line, but it's a good start. It's where we're starting off. We just want something to work on the GPU, and then see if we can make it work faster. So point number 1, make it run. Point number 2, make it run fast. So this was allocates data on the GPU. Output data, and this here was execute the Pi kernel. Then the final thing we have to do is download results. So let's do inside CPU is equal to numpy empty, and then it's going to be n points. That's the number of elements that we want in there, and we're going to have the d type is equal to numpy uint 32. So here again, the unsigned int here is really important, because up in my kernel, if I scroll up here, I'm calling it unsigned int. So every time you're passing data back and forth between the kernel and Python, you need to make sure that the data types match up. If this doesn't match up, so if I forget this one, if I forget it like this, I'm going to get garbage results. So we can look at that in a while, but let's try to get something to work first, and then see how we can break it by doing that wrong. So download the results first. We allocate the memory. So let's allocate memory to download 2 on the CPU, and then finally download from the GPU to the CPU. So that's CUDA mem copy host to device. And then we're going to copy to inside CPU from inside GPU. And then finally count the number of points inside. We can do a numpy sum of inside CPU. That should be it.
Sorry, just another question. Shouldn't it be device to host memory?
Yes. Device to host. Thank you. Thank you, Alfonso.
Okay.
It's actually not on purpose, but it keeps you guys on your toes to see if I'm making a lot of mistakes. Right. So it's the target, and then it's the source. And this should hopefully work. I'm crossing my fingers. Let's see if we can run this. Now this is a function, so we're not running it yet, so I'll just add a compute pi, and had the underscore GPU 10 or 100. Let's see if this works. And I actually realized that I've forgotten something. But we got an error. It's not alloc, but it's malloc. So let's find the line there and add malloc. What am I doing wrong? I'm in the wrong mem alloc, sorry. So it was mem alloc. There. Okay, so it compute pi GPU got an unexpected keyword argument block. And I think this
iPhone din først.
I think this is because I'm doing something a bit suboptimal here. So let me do compute pi GPU kernel up there. All right, because I call the Python function the same as my kernel module. So let me fix that bug immediately. That means that I have to compute the kernel down here, and then hopefully we're bits further on. Good. We've got something at least. It doesn't crash anymore. But let's look at our estimate and see what we're actually doing here. Okay. I'm generating 128 points. And I'm not using the 100 here at all. So this 128 should actually be n points. That should fix some of it, but still it's something's off. So let's see what I may be doing wrong. Do the kernel. Let's see the kernel first, okay? We generate some random numbers. We compute r, the origin, the radius from origin. And if it's less than or equal to 1, we set it the inside to 1. Otherwise, we set it to 0. It looks good. So what I want to do now is actually see what I'm doing wrong by perhaps plotting some results. So plt plot inside CPU. Now this is just by adding this into my function right now in Python. I should be able to get a plot from matplotlib, which tells me it should be zeros and ones, and that should be all it has. And it looks good, right? It has some points which are outside the zeros and inside 1. So what is still wrong? $78 should be the number of points inside. And the number total is a very large number, so I've done something wrong. Endpoints. Huh. Do you guys see what I'm doing wrong?
I don't know, maybe the end total is the same that we defined earlier.
It looks like it is. Oh, I've called it endpoints. Classical mistake. Whew. I'm tearing my hair out. I called it endpoints, and I'm actually calling it end total at another point. So end total should be there.
Maybe it's better that you change and the other one.
You're right, Luis Miguel. And points there. Let me do that on the in total endpoint. So I did the same mistake here. Okay. Oh, something's... Yeah, I did something... I did a total... There. Oh, now I've really done it, or... Yeah. Okay, so compute pi CPU still sort of works. Good. Let's go back to our GPU function now that we fixed it, and hopefully we get something which is more or less right. 3.12. That's good. And I can remove my debugging. 3.12. Let's do 200. 3.60. Let's do 300. 500. Let's do 1,000. Let's do 10,000. What happened? Any ideas?
Memory?
Well, 10,000. I think the memory on this GPU is quite. It's a powerful GPU. I think it has like 24 gigabytes of memory or something. But CUDA func set block shape. I'm using a block shape with 10,000 threads. That doesn't work. I cannot use 2,000, I think. I think I can use 1536. 5.
They,
I think that the maximum is 1024.
Oh, you're the expert. 1024, right? So that...
Jose Miguel is...
Sorry?
Jose Miguel is the expert. He said that yesterday.
And so this is, of course, not good enough for us, right? So we need to do something better. Now we have something that seems to work, though. This is my version 1. So let's just keep this in the back of our mind. This was version 1. It works. Now what I want to do, and we have about 20 minutes left before we have to round off for today. I want to optimize this. So now we've only used a single block. Let's use multiple blocks. That should be quite easy to do. Right? So if you look at this already here, it has potential for using multiple blocks. So let's fix that already. And we can do that in this this section down here. So num blocks and threads per block. Let's do 512 threads per block, and number of blocks is then number of points double divide by threads per block. And the double divide, that's integer division. So let's do threads per block and num blocks. Okay, the thing that I require now, assert n points modulo threads per block is equal to 0. I need to make sure that it's divisible by 512. Without that division, it's not going to work. So let's do 512 multiplied by 10. Oof. So let's see what did I do something wrong? 512 is correct. Times 2. Sorry. Okay, there's something fishy going on here. Number of points Was this the... No, it's number of points. And block dimension, it's thread index.y. So block index.x. Okay. Sorry. I made a mistake in the indexing here. And this means that when I was actually doing my calculations now, all of my thread indices, they were just ending up in the first section of the array. And the last section was just filled with garbage. So I think I fixed that bug now, just by looking at my own source code. So I'll recompile the module and try to run it again. And it seems to give better results. So let's do multiply by 10, by 100, by 1,000, 10,000. You see it's very, very fast compared to, well, now it's starting to struggle a bit more. Okay, so we got to slow with 512 threads. That's when it started getting slow. So this is version 2. Version 1, maximum 1024 threads. Version 2, it's slow with that number of threads. Let's make it faster. Any ideas on what we can do? What have you learned in the course so far to make this one run? So let's, let me do, I'm going to go to the top here and I'm going to import time. And then I'll do tick is equal to time. Talk is equal to time time. Print. Okay, so I'm gonna print the compute time so that I get the number, and print time taken. Talk minus tick. I hope this works. Okay, so 1.5 seconds. Slow, 1.5 seconds. Any ideas? How can we make this run faster?
We could try with the shared memory through the processors inside the GPU.
Shared memory. Excellent suggestion. Let's try using the shared memory. Now, shared memory is something that we need to make sure goes into our kernel. I may mess up things here now, so I'm gonna copy this one and save it, for example, here, so that I have something to go back to. And this is the thing about live coding. So this is version 2 is equal to that. But let's try fixing the shared memory. Now shared memory goes in something like shared unsigned ints inside shared 512. Okay, so this gives us 512 points, which we can compute stuff in. Okay, so, and this is shared memory. And the reason we're doing this, let me go back to the camera here and show you, is that right now what we're doing is that we're having the CPU over here, and we're having the GPU. It's a powerful GPU with 2 fans. And what we're doing is we're transferring all of the data. We're transferring the zeros and ones, the number of points which are inside or outside the circle. And that's a huge waste. We're transferring 512 million elements over there. Times 4. That's the number of bytes that we're actually transferring. So it's a big transfer. And this is the PCI Express bandwidth, which is relatively slow. This is a slow bandwidth, which means that we want to avoid this. So if we can do shared memory reduction, we reduce memory by a factor of 512. So that means that this one goes down to 1 million times 4 bytes. So it's a very big improvement in the number of bytes we're transferring. And in this application right now, this is one of the big things that's taking a lot of time. So let's see if we can do something on this. And right now I have to actually cheat and go to my my shared memory reductions for time, because I'm not going to go through the way to do it with you guys, because it takes a bit of time to explain it. Okay, so now I've copied my cheat code. So what we did first, we created this inside shared. We leave everything else the same, and then we do the inside shared. Inside shared. And I'm going to create a new variable as well. Well, this is essentially we're going to create 2 variables. One is the thread ID, and that's just going to be the thread index. And the other one is the block idx.x. So now the point is, by reducing, if we go back to this drawing, right? I said that we're reducing this 512 million bytes into 1 million bytes, because now each block is just going to write out a single number. It used to write out 512 numbers, but now it's just a single one. So block used to have 512, but we're going to reduce them down to a single one. And we're using the thread ID, which goes from 0 to 512 to index into this shared memory. And we're using the block ID to access into the global domain, which has now 1 million elements. Right? So the block ID goes from 0 to 1 million, and the thread ID goes from 0 to 512. And you multiply them together, you get the full 512 million elements. Okay. So that was the reasoning behind there, which means that this indexing now inside the shared memory, which is 512 elements, works because we're using the thread ID, which goes from 0 to 512. And now we're going to add this shared memory reduction and it's just going to come like boom. There it goes. And of course, I called it maximum shared. Okay, so I copied from the wrong place, but we're going to use inside shared. So inside shared is good. Inside shared is equal to plus inside shared of this. So the essence here is that we're taking an element here and plussing it with an element there. And if you look at the next line, where it's reduced from 256 to 128, we keep this element, but we plus it with this element. We keep this element and plus it with this. And by doing that, we reduce all of these 512 elements down into a single minimum, a single count. So I'll do the same with this one. Now it's going to be 128. And then it's going to be 64. And then when we're inside a single warp, we can do this much more efficiently. So we can just use it without async threads in between. So I'll do that 32, 16, 8, 4, 2, 1. It will almost be a miracle if this works without any mistakes, to be quite honest. And it was supposed to be P in all of these, of course. And this is technical compiler stuff, why you have to have the volatile float star P. And it's a volatile unsigned int P. Some technical stuff, but let's just ignore it for the moment and say that, well, we did some shared memory reduction. Okay? We generated some numbers. We had 512 of them. We reduced them down to a single number, which is the count. How many points were inside for this block? These 512. And now we're going to write out to the global memory out here. And that's if thread index 0, then we're going to write output of, and the variable was called inside of block ID is equal to P of 0. Hopefully, crossing fingers, we've done everything right. And we can compile this. Okay, it compiled. I'm happy so far. And let's see what we actually have to do here on the CPU side with the Python version. In this here, where we're allocating memory on the GPU, here we need to divide by 512, by this number here. So the threads per block. Okay, and then I'm gonna add the assertion up there as well, so that things stop before we allocate things. Now this makes sure that we're allocating far less memory. So we're, instead of allocating 512 million bytes, we're just allocating 1 million bytes. And other than that, the size here is the same. The inside CPU, that needs to change. So that's the number of points, double divide by threads per block. Again, because we're using fewer number, 512, a factor 512 fewer. We copy, we do the same stuff, and everything should run the same. Okay, help me now. Cross your fingers, and we're gonna press Shift Enter to execute. Whew. It worked! Wow! Wow! This was, we got it. So, version 3. Less memory. 512 in seconds. that was a great improvement. It went from terrible to less worse. But now we can actually do something. Does it work with this many? 2.41 seconds. So we could actually do 100 times faster, or 50 times faster with this one. Okay. Next challenge for me. How can we make this faster? Well, let's make each thread do more work. A trick here. Let's add another one. Iterations per thread is equal to 1000. Let's just pick a number, and then we're gonna do multiply by iterations per thread. So now we're just checking some stuff, and what I'm doing now is this iterations per thread is something that I'm gonna get in here. Let's just hard code it. I'm gonna hard code it because we're running out of time. I'm gonna say that we're gonna do this in a for loop. Okay. For int I equal to 0, I less than 1000, plus I. Okay, I just added a for loop. Now it doesn't help that I'm doing these kinds of things, setting to 0, 1, 0, 0, 1, 0, 1. I need to count it up. So what I'll do, I will do unsigned int num inside is equal to 0. And I'll just plus that one with 1. And then finally, after this for loop has run, I'll say that it's going to be num inside. Okay, so now each thread does 1,000 darts, throws 1,000 darts. It used to throw just 1, now it throws 1,000. And by doing that, we're increasing the work and reducing the memory traffic again by a factor of 1,000. So now we've reduced it by a factor of 512,000 just by these two things. We need to do a bit more CPU work to make this work. Oh no, please. Expected a semicolon. Okay, that's easy to fix, I think. There, missing the semicolon. This is often when you're working from Python to C++, Python to C++, you're mixing up and forgetting the semicolons and so on. Iterations per thread, it goes into the number of points there. And then we need to do this again for the size of the number of elements we're allocating. So again, allocate, double divide by iterations per thread. And then I'll just make sure that we're doing this in the right order. And the same down here, that we're gonna do the CPU version, divide by iterations per thread. And now let's see if it works again. Illegal memory access was encountered. Okay, I did something wrong. Okay, but you get the point. I will fix this for tomorrow so we can recap and go through the final stuff there, because this might take me 2 seconds or 10 minutes just to figure out what I did wrong. But the essence is that we looked at an application which was kind of slow on the CPU, made it faster on the CPU. Moved it to the GPU, it's really much slower, and it doesn't work for more than 512 or 1024 threads. And then we start optimizing. And working with optimization here in Python is really efficient. I would not have been able to do half of what I've shown you now if I was using C++. So, in summary today, I would really like you guys to do the homework, which is to install the software here. Install the Anaconda stuff, get the environment up and running, and test that you can get Jupyter Lab up and running. And I will send you out an email with a a kind of Hello World Jupyter notebook that you can test for yourself and see if things work on your computer. Okay?
Okay.
The thing is that if we don't have like an NVIDIA GPU card, it's going to be like impossible to produce the environment.
Yeah.
I think that using the nodes that Jose Miguel provides us, it is going to be impossible to access the Jupyter URL.
I see your point, but I think Jose Miguel has a server which I hope we can install this on.
When we deploy like the Jupyter Lab,
Yes.
Yeah,
it is
we are
already
testing
on
it
board.
via SSH.
Yeah, exactly.
Yeah.
So,
So-
we don't have like a remote desktop to work on something like that.
We will figure this out for tomorrow, and I will do my best to help you set this up. And hopefully, I have a backup solution where we can work a bit tomorrow interactively as well. But you're gonna have a good, hopefully, a good learning outcome, even though it's not gonna be as interactive if you have your own computer working with it. Okay?
There is no way to simulate the CUDA programming AMD card, right?
No, not really. Not in a good way. Unfortunately. Okay, but this was roughly what I wanted to cover today. The thing that we didn't cover as much was the floating point issues. I think it's worth looking into. This video here, session 4, floating point. I don't remember how long it is, but if you have, if you're bored and want to learn a bit about how computers work, I would really recommend watching that video. If I had seen that video 10 years ago, it would have helped me save a lot of time, to be honest. Okay. Any questions for today? And thank you, Luis Miguel, for the comment. I'll make sure that I take that into consideration about the access to NVIDIA GPUs. Any other comments?
It's been an interesting class. Thank you.
Thank you, Luis Miguel.
Thank you.
Yes, I agree.
Good to hear. The slides and everything what we've gone through today is on the webpage, so you can take a look at it there. And Jose Miguel, do you want to finish off with some concluding remarks?
No, only to say that, of course, there is a problem with the access of several students to the NVIDIA GPU in order to program all these Jupyter Lab examples, because the main problem is they are not able to use the Jupyter Lab remotely, I think.
Is Python installed? Because maybe we can reproduce them.
I can install Python.
Okay.
I can install Anaconda, but the problem is the Jupyter Lab. It's
Yeah,
not
but
available.
at least being able of executing Python script would be helpful, I think.
Okay, I'm going to try the installation of Anaconda in HGPU cluster. Okay, in particular in one node, in compute file node. Okay, in order you can test the examples in Python. Okay.
And if things don't work out, the good thing about Jupyter Notebooks is that it's extremely easy to export as Python scripts. And then you say, well, Python scripts don't help me at all. They do help you, because if you only have C++, having a Python script that it's the kernel source code is the same. So the CUDA function is exactly the same in C++ as it is in Python. So it does help you a bit. But let's see what I can make work for tomorrow, so that we can get a good interactive session where everyone can do some coding as well.
Okay.
Good. Then I thank you all for today. Jose Miguel.
Thank you, Andre. I thank Professor Broadcourt for your good presentation and lecture. And tomorrow we'll continue with the sessions. Okay. Thank you, everybody. We'll see us tomorrow at 4:30. Okay, in the same room. Okay.
Very good.
Yeah.
Thank you so much, everyone. I'll see you all tomorrow.
Thank you.
Thank
Bye.
you.
Thank you. See you tomorrow.
Bye.
Bye.
Bye.